Hello students, let's talk about one of these problems where we paint a surface and talk about the volume of the paint on the surface. For instance, first of all, I guess this is now a fifth video in differentials. Whoops, that's supposed to be a 5. And let's suppose that we wish to paint the side of a cylindrical grain silo. Right? The thing looks like this. And we want to paint it. The height is 90 feet. Don't need to write it. Just put it right here. The height is 90. The diameter is 32. Well, if the diameter is 32, then the radius is 16. There's the 16. And the coat of paint is going to be 1/8 inch thick. So by the way, these are all feet. This is 90 feet. This is 16 feet. And so when the paint is 1/8 inch thick, well, we got to convert that to feet. And there are 1 foot is 12 inches. So to get the units to line up here, I need to have inches downstairs, so the inches downstairs cancels with the inches upstairs here. This is 1/8 times the 12. Well, this is 80 and 16. This is a 96th. A 96th of a foot. So look, I often talk about the differential being like an error, but I mean, it's the same notion to say we think that the radius is 16, but when we paint on a 96th of a foot, that's going to increase the radius by a 96th of a foot, right in there. So, the new volume of this thing is going to be like out here, right? It's going to be like somehow wider. And when you paint that, it's going to, increase the volume. But remember, we don't want to know the volume of the whole thing. We're not filling up the whole thing with paint. There's just the paint on the outside. We just want to know the volume of that 1/96 inch thick layer of paint. But the idea is we're thinking of the volume as having increased from, here, let's get on with this while we talk about this. The volume of this cylinder is pi r squared h, but the h is 90, and that's not going to change even when you paint it, because you're only painting the sides, it says in the problem. So this is really then 90 pi r squared. Now, it's the same notion that we often talk about, where you got a function and you got some value x, and we're thinking, that the y value was f of x, but in actuality there was like this little bit delta x. This is the 1/96th. We're increasing from 16 to 16 plus a 96th. And so the volume is really going to be up here at f of x plus delta x. So this right here, what I usually call the error, this is going to be the volume of the paint. Because see, when the radius changes from x to x plus delta x, the volume changes from here to here. Well, that little bit that the radius changed by, this is the 96th of a foot that the radius changed by. And that's going to cause the volume to increase by this much. This is the volume of the paint. Now, what we usually say is, like, this is an error, right? This bit here, well, okay, formally this is delta y, but we've already said we approximate this with dy. We approximate it with dy. So the dy out of this problem, in this case it's going to be dv, because I've labeled the y variable v. The dv in this problem, this is the approximate volume of paint. If you wanted to know the exact volume of paint, you could just take the volume, the exact volume of paint. That would have been, evaluate the volume at 16 plus a 96th. There's the volume you know, up here, and then I subtract the volume of the silo, well, that's 90 times pi times 16 squared, right? This would be the exact volume of the paint, because the volume, right, the volume is up here. Once you put the paint on, the volume was down there without the paint. So this is the volume of the paint, the difference in f of x plus delta x minus f of x. See, this is v of r plus delta r minus v of r, where, you know, r is 16 and delta r is a 96th. But this is the exact volume of paint, and I understand, you know, we should find that, but it's, you know, for reasons it being the 1600s, it's the operation here is we approximate delta v, this exact volume of the paint. This is delta v. This is how much, right? This exact amount here. This is delta y, right? And we approximate delta y with dy, which is how much the tangent line rises by, right? dy is from here to here, delta y. Anyways, to tell you the truth, I don't really want to make another video. I think that this is all okay. It's just, I guess I'm just getting fatigued about repeating it, but I don't mind. I want people to get it. So what we do is we approximate delta v by dv. So in other words, you know, when I say v of r plus delta r approximately equals v of r plus dv, that's what I'm, this part here, this is the paint, this is the volume of the paint, because this is the volume of the silo. Think about, you know, you got to think it out here a little bit. When I put in r, when I put in 16, and I'm computing the volume of the silo. When I calculate, you know, when I add something to that, I'm adding now, you know, when the radius went from r to r plus delta r, the volume went from, you know, v of r to v of r plus delta r. That change, that's the change of volume. We computed it explicitly up here, but, right, we can compute that explicitly, but we approximate delta v by dv, so, you know, we're using this. The dv, this is what's replaced the delta v. This is the volume of the paint. It's dv. Now dv, well, dv dr equals v prime of r. So multiply both sides by dr, and dv is v prime of r dr. So this dv that we're looking for here is v prime of r dr. It's really just that. Now we might as well find v of r also and talk about this in a moment. So this is the volume of the silo. This is the volume of the paint, the approximate volume of the paint. So remember now, r is 16. V prime here, well, since v is 90 pi r squared, then dv dr is, well, we're going to just say v prime of r dr. So we're saying v prime of r, right? v prime of r dr. So let me just call this v prime of r. Then v prime of r is going to be 2 times 90 is going to be 180 pi r. So this part here, this v prime of r, well, remember, r is 16, so this is 180 pi times 16. And then dr is the 96th. So when you do this out, let me get my calculator. So when you do this out, you know, formally you should keep it with pi's and everything, but I'm just going to get an approximation on this to a few decimal places. We got 180 times pi times 16 divided by 96, and this gives us about 94.25. Times pi times 16 divided by 96. Of course, you know, if I wanted to keep, you know, which is, by the way, I could have gone like this. I could have gone 180. I could have gone 180 times 16 divided by 96. And that's 30. So this is 30 pi. Now I can take that, multiply it by pi to get an approximation. This is 94.25. Right? That's the volume of the paint, 94.5 cubic inches. Here, V of R, this would be the volume at 16. Had the radius been just 16, the volume would have been the volume at 16. And the volume at 16 would have been 90 pi times 16 squared, right? Because the volume is 90 pi r squared. So V of 16 is going to be 90 pi 16 squared. So that looks like 90 times 256, which is 23,040 pi, which, by the way, is approximately 72,382.29. So see, there's the volume of the silo plus the volume of the paint. Now remember, this isn't the exact volume of the paint. This is the approximate volume of the paint because we approximate delta V by dV. This would be the exact volume of the paint, but that's not what they want. They want the approximate volume of the paint. Now, when you talk about your relative error, it's dy over y, right? In this case, it's dV over v. Well, this is dV, the 94.25, and this is your v, right? This is your estimated amount, 72,382.29. We could do it exacter if we just, took 30 pi over 2304 pi, because that way the pi's will cancel. So this is 30 divided by 23,040, and it's 0.0013, right? This is 0.13%. This is not even 13%, not even, it's like about 0.1%, 0.13%. This is the relative error. So it's, okay, again, I'm calling it relative error, but you could consider it, it's the ratio made by the volume of paint over the volume of the whole thing. Actually, in a problem like this, they wouldn't ask you for the relative error because there really is no error going on, right? But another way to think of this is when the radius increases from 16 to 16 plus a 96th, the volume increased by 0.13%, right? But we wanted to know the volume of the paint, and the volume of the paint is 30 pi cubic units, in other words, 94.25. So, just to wrap this video up, usually I say, we've got an x, we got a delta x, and we think of this as like, an error, right? When x goes from x to x plus delta x, we often think of that as an error in the measurement of x. But in this case, it's not an error in the measurement of x. It's just x has like this thickness of paint being added. The radius, right, has an x being added onto it of a 96. So we went from 16 to 16 plus a 96th, right? It's like behind the scenes here. The radius was 16. And then when we put the paint on it, now the radius is 16 plus a 96th. So here's the volume at 16, that's the volume of the silo. Up here, this is the volume of the silo plus the paint. We don't want the volume of the silo plus the paint. So we take the volume of the silo plus the paint, we subtract the volume of the silo. That leaves us the volume of the paint. Now the volume of the paint can be found explicitly right here. But remember, we approximate, right? We approximate delta y with dy. So that's why I'm approximating delta v by dv. And that's what we did all down here. All right.